about this is another machine learning talk about classifying frequently repeating fast radio bursts with unsupervised machine learning. This is a contributed talk, so therefore he will have 12 minutes for talk part, and then we have 3 minutes for Q&A. So Bo Han Chen, please start when you get ready. You need a full screen. Yes. Good.
Hi everyone, I'm Oliver from National Tsinghua University. Today I'm going to talk about two topics about using machine learning to analyze FRB. The first one is to discover the hidden repeating fast radio bursts. And the second one is an analysis on the crazy FRB, FRB 2011-24. First, let me start from the analysis of discovering hidden repeating FRBs with unsupervised machine learning. This work has been published on the journal Royal Astronomy Society. Okay. First, let me start from the question I'm trying to solve today. We know that FRB are classified as repeaters and non-repeaters. This classification is important. It might imply different physical origins. For example, if today an FRB is a repeater, then probably it is from pulsar. If today a FRB source is a merger of neutron stars, then it is very unlikely to repeat. So doing this kind of classification is important for us to understand FRB. Okay, so it's important. However, we know that FRB repeating is definitely a repeater. But if FRB haven't been seen to repeat, it is still probably a repeater, but just humans haven't detected it. Probably this FRB repeats tomorrow, then finally we know that it is actually a hidden repeater. Okay, so here comes the most important questions. Is it possible to discover this kind of hidden repeating fast radio bursts without the expensive monitoring? In this research answers, yes, we can do this. Okay. The way we achieve this goal is using machine learning. First, we collect FRB catalog source from China FRB catalog. There are total more than 500 FRBs, and about 100 samples are the repeating FRBs. More than 400 are non-repeating FRBs. Okay. For each FRB, we collect certain physical parameters. So now we have 500 FRBs. Each FRB has certain physical parameters. We can equivalent this mathematically to 500 points in a certain dimensional space. Okay. Points in high dimensional space. Each point is an FRB sample. Then, with unsupervised machine learning model, UMAP, we project this onto a 2D plane, just like what Jasper had just expressed. Eventually, our machine learning projection resulting in the plane look like this. So, machine learning results here. The color points are the non-repeating fast radio bursts. The gray points are the non-repeating fast radio bursts so far. And clearly we see that the color points are all in the three main clusters, there, and there. Outside of these three clusters, there are almost no repeating FRBs. So here, we say that these three clusters are the FRBs clusters that have repeating properties. The rest of them are not. And meanwhile, we see the gray points are also there in these three clusters. So here we say that these gray points in these three clusters having similar physical properties with those repeating fast radio bursts. As a result, it is very likely to be our FRB repeater candidates. Okay, so we pick up those breakpoints. We pick out those breakpoints in these three clusters marked in blue. These FRBs are the repeated candidates we are looking for, and now we found it. So our conclusions. Our unsupervised machine learning method can classify hidden repeating fast radio bursts, as we just presented. And among the original 474 non-repeating fast radio bursts, 188 are classified as the repeater candidates. So it's 40%. Okay. After this paper is published, recently, China FRB team has released another new catalog about the repeating fast radio bursts. There are in total 25. In their new FRBs, there are only 2 that has overlapped with our previous catalog. These 2. And among these 2, one of them has been successfully projected by our algorithm. So this newly discovered FRB repeaters is the candidates that we have just identified in the previous slides, but the other one is a missing case. Okay, so chapter 2, classifying a frequently repeating fast radio bursts. 2011-24 with unsupervised machine learning. Okay, still, we know FRB are classified as repeaters and non-repeaters. For repeaters, most of them are not observed to repeat more than 10 times. But there are 2 crazy FRBs, 121102 and 2011-24, that have been detected by fast telescope for more than 1,000 times. These two FRBs are very special, so they are a target we'll analyze here. And 121102 has analyzed by Jasper, the last speaker, so this research is focusing on 2011-24. Okay, so we are analyzing these 2 FRBs. But here, we have a problem. If we plot all the physical parameters we can obtain from FAST catalog, we see that it is actually very difficult to do a manual analysis. We can see that for the waiting time, it has a double peak. So doing classification is possible if we cut it into 2 peaks. But for the rest of 7 physical parameters, it is impossible to make a feasible classification. And if we are only doing this on waiting time, then we are missing the rest of all the 7 physical parameters. So we need a way to do this, considering all the parameters. So too much data, but too little code for human. Now, the machine comes to help us again. Okay, still, FRB catalog from fast telescope. For each FRB this time, we have 8 physical parameters. Also, 1,000 FRBs with 8 features is 1,000 points in 8-dimensional space, then projected onto 2D pen. So the machine learning this time projected to a result like this. Okay. In this result, we see there are totally 3 clusters identified by the machine learning. One of the clusters is large and sparse, and the rest of them are 2 small but dense clusters. Okay. Then we have a classification now. Now we want to know what has driven the machine to make this classification. So we look into the data distribution behind this. Okay. From energy-related parameters, signal-to-noise ratio, peak flux, and fluence, we see a clear trend from the lower left to upper right, the energy going from low to high in these directions. Okay. And for the frequency-related parameters, the frequency going from low frequency to high frequency from the upper left corner to the lower right corner, these directions. Finally, for the time-related parameters, arrival time, equivalent wave, and waiting time, there are almost randomly distributed in our results. So we say that time parameters are not influential in our case. Finally, we compare the two FRB's results. One of these is done by Jasper, the previous speaker, and this is the results I present in this talk. Now the magical things happens. We see that these two FRB results actually having similar structures. Both of them have large and sparse clusters on the left-hand side and two small but dense clusters on the right-hand side, and even smaller clusters here and here. So we see these two FRB results from AI actually has very similar structures. So here we say that this similarity might have implies the similar physical mechanics driven these two FRBs. And that is the reason why the AI projected results are so similar. Okay, so the conclusion of chapter 2. Our machine learning has divided this FRB 2011-24 into 3 clusters. These 3 clusters are either high energy, high frequency, or low frequency, but time factors are not very influential in our results. And finally, and the most important result, the AI projection from FRB 2011-24 and FRB 12-11-02 are actually very similar. This could imply they are driven by similar physical mechanics. And as far as we know, this is the first evidence saying this. So that's all. Thank you very much.
Okay, thank you very much. We have 4 minutes for Q&A. So, do you have any questions from on-site people? Toya, please.
Hello, Oliver. So thank you for the good talk. I'm just curious, is there any common properties between your classified repeaters and the one repeater or Jasper's repeater? Is there any common properties between them? So, how could you conclude the two machine learning works together?
Well, the similarity is presented by machine. So the only similarity we have now is the machine learning provided results. Yes, and because actually the parameters me and Jasper using are actually a little different. So magically there is a coincidence on the two results. So we can say that eventually machine learning gives us the results saying that these two are very similar. But what makes these two similar? Actually, this is a black box there, because machine learning itself is a black box. So we cannot say that, physically, this and this is similar. This is not how it works. It is a machine learning combined result.
Okay, we can take one more question from both sides. Okay, there.
Hello, Oliver. Thanks for your interesting presentation. According to the last point, I'm curious. So, if there are two kind of FRB, if the classification result looks same, it must imply that the two FRB must have a similar mechanism, right? Or other reason?
Using must could be a term too strong.
Yes.
So the statement we can say is because the machine learning result is very similar, and this kind of coincidence has a very little probability to happen if these two cases are actually irrelevant. So that's why we are saying that these two are driven by the same mechanism. So saying that must, well, this is too strong, I think. But we can say it is very likely.
Okay, thanks.
Okay, thank you very much. So it's time to move on next talk. So let's thank the speaker again. Thank you very much.